Today, we're going to visualize and understand linear regression. The algorithm so fundamental that if machine learning were a school, linear regression would be the very first day of class. And like the first day of school, it looks simple. But get it wrong and everything that comes after gets confusing fast. Linear regression answers one question. Given some data, can we draw a straight line through it that lets us make predictions? You have house sizes. You want to predict prices. You plot them. They roughly follow a line. Linear regression finds that line, the one that best fits your data. So you can plug in any new house size and get a predicted price out the other side. The equation for that line is U equals y double times x plus y what's. Y what's is the slope. How much y changes for every 1 unit increase in x value what is the intercept, where the line crosses the axis. A steep positive slope means a strong relationship. A negative slope means as x goes up, y goes down. A slope of 0 means x and y have no linear relationship at all, and probably no business being in the same model together. The line doesn't pass through every point. Real data is messy. Each point has a residual, the difference between the actual value and what the line predicted. Positive residual means the model underpredicted. Negative means it overpredicted. The best fit line minimizes the total of all these errors squared. That is the core objective of linear regression. That total squared error is called mean squared error, or MSE. Plot MSE against the slope value and you get a U-shaped curve. The bottom of that U is the slope that produces the smallest prediction errors. That is where we want to be. Gradient descent finds that bottom. It starts with a random slope, measures the steepness of the MSE curve at that point, and takes a small step in the downhill direction. Then it does it again, and again. Each step the slope gets a little better and the MSE gets a little lower, until the changes become so tiny that the algorithm says, I'm done. Converged. Now here is where it gets entertaining. What if your data clearly followed a wave pattern and you confidently told linear regression to fit it? It would draw its straight line through the middle, survey the mess of residuals on either side, and essentially shrug. The pattern is nonlinear. A straight line cannot capture it no matter how much training data you give it. Always plot your data before fitting. This is not optional. It is rule 1. Multiple linear regression extends the idea to many features at once. Instead of one slope, you get one weight per feature. House size has a weight. Number of bedrooms has a weight. Each weight tells you how much that feature independently contributes to the prediction, holding all other features constant. Before you trust your model, check the 4 assumptions: linearity, independence, homoscedasticity, which means constant residual variance across all values of x, and normality of residuals. Violating them does not always destroy your predictions, but it does mean your error estimates and confidence intervals cannot be trusted. To evaluate how well the line fits, use 3 numbers together. R squared tells you what proportion of variance your model explains. 1 is perfect. 0 means the model is no better than just predicting the mean. RMSE gives the error in the same units as y. MA is more robust to outliers. Report all 3. One number alone can flatter a bad model. And then there is overfitting, the villain of every machine learning story. Fit a degree 9 polynomial to 10 points, and it will pass through every single one, boasting an R squared of 1 on training data. Show it one new data point and it reports a negative R squared. Yes, negative. We have seen it happen. Ridge and lasso regularization prevent this by penalizing large coefficients, keeping the model grounded in reality rather than memorizing noise. The Sklearn workflow takes 3 lines. Split your data. Fit the model. Predict and evaluate. Model.cof underscore gives you the slopes. Model.intercept underscore gives you y with on. Model.score gives you R squared on any data set you hand it. Thanks for watching. If this helped, like, comment, and subscribe.